Okay, let's continue with the discussion of composite solid propellant modeling. What I want to discuss now is how to account for the effect of aluminum addition in composite solid propellants. Before I go into the details of the model, I will just give a quick recap of the basic modeling approach that is being used, which is a serial burning approach. Okay. What I did not explain in detail when we spoke about this last time is why serial burning and why not parallel. Let me just explain first what I mean by serial and what is meant by parallel. In the serial burning approach, what we have been doing is to look at lines passing through propellant like this, okay, and the question that we are asking is that if we ignite this section of the propellant here at the top, okay, how long would it take for it to burn through this length L? Okay. The burn rate of the propellant is taken as, in this case the burn rate of the propellant is the length L divided by time. Okay. This length, as you can see for this line that I am highlighting now, okay, this line, along the length of this line there are particles of different sizes, and we already saw that because the oxidizer to fuel distribution is different for different particle sizes, larger particles are generally oxidizer rich, smaller particles are fuel rich. Okay. Therefore, the burn rate of each particle size is different, and therefore the time it would take for different segments of this line to burn will also be different. Okay. So, if you look at this particular line, it intersects some larger particles here. For example, this is a large particle that it intersects, this is another large particle that intersects. Between these two larger particles, it goes through a segment of smaller particles. Okay. So, the time for burning of this line will be the sum of the time for each of these line segments composed of particles of different sizes. Okay. So, this will be the sum of the time, and that time we saw is the fraction of the length occupied by a particle of a particular size, which we called as Li, divided by the burn rate of it. Okay. So, this is the basic idea of the serial burning approach. Okay. Now, what is done is, of course, if I took a different line, I will get a different burn rate, or I may get a different burn rate. It can be higher, it can be lower. So, the propellant burn rate is simply taken to be the burn rate of the statistically averaged path or the statistical particle path, which is nothing but we take a large number of such lines, okay, and then average the number of particles of a particular size that occupies a fraction of that line. Okay. And as it turns out that is simply proportional to the volume fraction of that particular size. Therefore, Li will be proportional. Li is the fraction of an averaged line occupied by a particle of size di will be simply proportional to the volume fraction of that particular size di. So, if you draw a random line through a cube containing spheres of different sizes, the probability that the line intersects a particle of size di is proportional to the volume occupied by that particle. Okay. So, this is the serial burning approach. Yeah. Total time for a line, for the average line. Yeah. You can do it in, see, because the way the averaging is done, if all the lines are of the same length, I can calculate the time for a large number of lines and then average it. Instead, what we are doing is we are calculating the average line and calculating the time for it. It's essentially the same. Yeah.
But the frequency is just like sum of the times.
Sum of the times for individual particles of a, it is a sum of the times for different particles. For example, 20% of the line could be occupied by particles of size 200 microns. Let us say, okay, I think just for clarity I will give one example. Let us say we have such a average line. It is possible that, let us say, 1/4 of the line is occupied by particles of size 200 microns. Okay. Let us say another 1/4 is occupied by particles of size 100 microns. Okay. Let us say the rest of the line is occupied by particles of 20 microns. Okay. Let us say this is the statistically averaged path for the propellant that we are considering. It has 25% of the line occupied by 200 microns, another 25% occupied by 100 microns, the rest 50% occupied by 20 microns. So, the burn rate for this propellant would be the length of the line, which is arbitrarily taken to be 1. You can scale so that the number of particles are appropriately scaled, divided by the sum of the time. Okay. The sum of the time in this case will be 0.25 divided by r dot of the 200 micron particle plus 0.25 divided by r dot of the 100 micron particle plus 0.5 divided by r dot of the 20 micron. That is it. Okay. This will be the burn rate. Okay. So, that is the serial burning approach. Okay. Let us look at the other approach, which is called the parallel burning approach. In this, instead of, we imagined in the serial burning approach case that the question was that if we ignited the propellant at the top, how long would it take for this length to burn off? Equivalently, in the parallel burning approach, the question is if we ignited the propellant on the top here, this entire, if we ignited the propellant here on the top, okay, what would be the mass flux of the gases that come out from that section? Okay. So, here particles are burning in parallel, here particles are burning one after the other, and therefore it is called serial. Here we are igniting the top of the propellant, which I have hatched here. The question is, if we ignited this at various instances of time, how much mass flux will come out of the surface? Okay. That mass flux divided by the average density of the propellant will be the burn rate of the propellant. Okay. Here the burn rate of the propellant or the mass flux coming out of the surface, rho p r dot, will be the sum of the mass burn rate of particles of different sizes, mass flux multiplied by the area, the surface area of each one of these particles, okay, divided by the total area. This will be the mass flux. Okay. So, here also of course the heterogeneity is accounted for. For example, you have different particles, here you have a large particle, here you have some small particles, okay, they will burn at different rates. Okay. And for example, it is possible that the larger particles which are AP rich will burn at a rate that is closer to that of AP. Moderate size particles which are almost stoichiometrically mixed will contribute a lot of mass flux, and very small particles which are fuel rich may contribute less mass flux than the stoichiometric. Okay. One issue with this is that, or one issue which was identified with this approach, this is the approach that BDP model used. Okay. The weightage that is given to a particle of a certain size is proportional to its surface area, okay, and all the particles are assumed to regress at about the same rates. Okay. So, in the vertical direction, they contribute different mass fluxes in this direction, but the surface regression will be limited by the slowest burning case. So, the weights are assigned using the surface area, and therefore, as you can see, if you have see this, the stoichiometric spots will burn faster, the AP rich parts will burn slower, so will the fuel rich parts. Okay. So the conclusion from this approach was that the weights assigned to smaller particles were usually higher. Okay, that is a conclusion that came out of this approach, that the weights that are assigned to smaller particles, which smaller particles are stoichiometrically burning particles, are usually higher than the weights assigned to this. Okay, so what happened was that the burn rates were typically over predicted, and so were the index. So especially in cases where the AP distribution was very wide, that you had a bimodal or a trimodal distribution with very large AP sizes, moderate AP sizes and very small AP sizes, the burn rates were always over predicted because the weights that were assigned to the faster burning particles were always higher. Okay. But in this case, if you see, the weights come through the time contribution of the particles, and therefore even if you have a large fraction of faster burning moderate size particles, the time contribution of that, okay, will be smaller, because the time contribution for that segment will be the length fraction divided by the burn rate. Okay. So larger the burn rate, smaller is the time contribution from that particle. So this approach seems to capture this behavior accurately, where the weights are correctly assigned. The weights that are assigned through the time estimates seem to be more appropriate for a realistic situation than the weights based on the surface area. Okay. So this is a quick recap I thought I will give you on why we are adopting the serial burning approach, what serial burning approach is, and why we are not using the parallel burning approach. Okay. So with this, let us move on to the effect of aluminum. Okay, the extension of the heterogeneous quasi 1D model to include effects of aluminum. Little bit of background actually, I would like you to look at this plot. What is shown here is the same composition, okay, which is if I remember right, a 68% AP, 18% aluminum and rest is HTPB. The same composition, but what is changed is the aluminum particle size. The aluminum particle size is changed from 30 microns to 15 microns, then to 3 microns and all the way up to 0.1 microns. Okay. So the 30 micron and 15 micron are typically the sizes that are used in practice. 3 micron can be considered an intermediate size, and 0.1 micron belong to the class of ultra fine or nano aluminum. Okay. What is observed here is at pressures of both 34.5 atmospheres and 69 atmospheres, changing from 30 micron to 15 micron has no effect on the burn rate. Okay, the burn rate remains roughly the same. 3 microns, you can see a small increase in the burn rate, and the burn rate increase or the burn rate change with 0.1 micron is dramatic. Okay, the burn rate goes up by factor of 4 or 5. Okay. So the conclusion from this is that changing AL particle size from 30 micron to 3 micron leads to marginal burn rate increase. Submicron sized aluminum or ultra fine aluminum dramatically increases the burn rate. It is in fact 5.5 times the burn rate with the conventional aluminum. The 30 micron and 15 micron are called conventional aluminum, the 0.1 micron is called the ultra fine aluminum. So ultra fine aluminum, this is an important point because it is known that processing a propellant with 18% nano aluminum can be quite difficult because of viscosity issues. So what was done in the study by Doken et al. Is they, instead of substituting all the conventional aluminum with ultrafine aluminum was substituted in smaller quantities, and they found that ultrafine aluminum increases the burn rate significantly. Instead of 5.5 times, about 3.5 times, even at 20% substitution of the conventional aluminum. 20% of the 18% aluminum was substituted with ultrafine aluminum, and they found a burn rate increase of 3.5 times. Okay. What does this mean? Okay. So large aluminum particles, that is greater bigger than 10 micron play a passive role. They do not do anything close to the surface to affect the heat flux that comes to the surface to have an effect on the burn rate. So, there is no oxidation of aluminum close to the surface, and therefore, large aluminum particles, here large is greater than 10 micron, can be treated as inert. As far as the heat flux, as far as the effect of those particles on the surface heat flux is concerned. Of course, they go downstream, react, release heat and contribute to specific impulse, but they do not play any active role close to the surface. On the other hand, ultrafine aluminum plays an active role. It oxidizes sufficiently close to the surface, increasing significantly the conductive and radiative feedback, and therefore the dramatic increase in burn rate that is observed. Okay. One mechanism that is suggested for the effectiveness of ultrafine aluminum as opposed to conventional aluminum is, if you look at the burning of a conventional aluminum particle, both these particles have an oxide layer coating on top of it, and for the 30 micron aluminum particle with the metallic aluminum in the core, the surface with aluminum oxide, the metallic aluminum becomes accessible to oxidizing agents only after the outer oxide layer has melted and vaporized away. Okay. On the other hand, if you decrease the particle sizes to nano sizes, we know that the surface to volume ratio increases drastically, and therefore the volume expansion because of the melting of the aluminum in the core is thought to actually crack open the oxide coating, thereby exposing metallic aluminum to the oxidizing environment very close to the surface. Okay. So, this is thought to be the mechanism for which can explain the dramatic increase in burn rate. Let us look at the effect of conventional aluminum of the kind that is used in the space boosters, also used in propellant TPH-1148, which is used in the space shuttle booster. The APE is 68%, nominal size is 200 microns. Aluminum, as you see here, is quite large, it is 50 micron, okay, 18%. Burn rate at 42.5 atmospheres is 9.3 millimeters per second with an index of 0.311 and temperature sensitivity of 0.11% per Kelvin. Okay. The aluminum particle size, like AP, is also log normal. Okay. As a first step in understanding the effect of aluminum, the following assumptions are made based on the conclusions we arrived at from the data shown in the previous slide, that all aluminum particles in the propellant are inert as far as conventional aluminum is concerned. This implies that in the space shuttle booster propellant, the propellant itself can be considered equivalent to a non-aluminized propellant with 68% AP and 14% HTPB, which is equivalent to a non-aluminized propellant with 82.9% aluminum, 82.9% AP loading. The only extra effect that needs to be accounted for is the energy that is used for heating up and melting of aluminum as it goes through the surface, goes through the condensed phase and into the gas phase. Yeah. Yeah.
So, as you said that if you use the aluminum or the 10 micron particle, it acts as an inert. So, how it increases the thrust? Is this only by
it will increase the final temperature of the gases also. It will not have a significant effect on the molecular weight. If at all, it will only increase the molecular weight a little bit, but that is not the point. What the significant effect comes because of the increase in the flame temperature, the final equilibrium temperature.
Okay.
Yeah.
The other question is, what is the heating time if, let us say, I have a 10 micron particle and a 1.1 micron particle? The heating time for both the particles remain the same?
No, it will be different.
For the small particle,
small particles will heat up faster. Yeah. Small particles will heat up faster. Be proportional to d squared. I mean, inversely proportional to d squared. Smaller the particles, faster will be the heat. Yeah. I am sorry, proportional to d squared. Whatever I said first is correct. Yeah. It's just conduction problem. Larger the size, more is the heating time. Yeah. So, the equivalent propellant or an alternate interpretation of the assumption is that in the serial burning approach used in the heterogeneous quasi-1D model, statistical particle path is taken to consist of binder matrix coated AP particles of various sizes. For propellants with aluminum, the statistical particle path can be taken to consist of AL particles in addition as well. If these inert AL particles are assumed to get ejected into the gas phase as the line burns, then the time contribution of the aluminum particles to the total burn time is 0. This makes the statistical particle path equivalent to that of a non-aluminized propellant as indicated earlier. But remember that the heating up and the melting enthalpy are accounted for as it goes through. Another strategy would be to simply homogenize the aluminum with the binder and take care of it. That is also something that is tried, and it is equivalent to what is described here. So, predictions with this assumption are shown here. The predicted burn rate and the index match well with the experimental measurements. The predicted temperature sensitivity is 0.07% per Kelvin compared to the measured value of 0.11% per Kelvin. Anyway, let me mention this. In the model, the data that is used for estimating parameters is the data that is available for ultra pure AP. It is known ultra pure AP burns at 3.3 millimeters per second at 20 atmospheres with surface temperature close to 870 kelvins and has a temperature sensitivity of 0.16% per Kelvin, between 0.16% per Kelvin to 0.18% per Kelvin. It is known that impurities present in AP increases the temperature sensitivity. Okay. So, the reason why the predicted temperature sensitivity is lower than the observed temperature sensitivity is that the AP that is used in the actual propellant will have some impurities in the form of potassium or sodium depending on the route that was used to synthesize ammonium perchlorate, and therefore may have had a higher temperature sensitivity. What this means is that at least in defense applications where as low a temperature sensitivity as possible is preferred, the best strategy seems like to use ultra pure AP to minimize or to keep the temperature sensitivity at a minimum possible value. Yes, sir.
So actually, in one of the recent static tests of solid dopage testing, we found that one of the cascade motors in 2005 to 6 stages had a very low burn rate when compared to the prediction.
Okay.
And is it because of the aging, some burn rate can modify, and what are the ways that we can avoid aging rate with respect to solid dopage?
Okay, that is a separate field of investigation in itself. If this is what you are saying is based only on one test, I don't want
some 8 to 10 tests because we had a problem with one of the machines. So
okay.
It happened that we found that one of the machines is not meeting the requirement. Then subsequently we tested a lot of earlier cascade process.
All from around the same time?
Around the same time, and
okay.
we found we have the same behavior.
Okay.
Having a reduced burn rate.
Okay. If you have fired some 10 motors from the same
I don't know the number exactly.
Around the same time and get about the same burn rate, it is likely to be because of aging. Yeah. And I mean that's about all I can say. Yeah.
Does the propellant have some catalyst?
I don't know.
What I mean is there are life-related issues with some of the catalysts like copper chromide, which actually decompose over a period of time, and therefore the effectiveness in trying to modify the burn rate is huge.
Yeah.
Therefore, it's possible that so-called aging is related to that catalyst. It is known in VSSC. Some attempts are being made to examine that question.
Yeah. And more predictions for propellants, aluminized propellants with no iron oxide, micron sized iron oxide and nano iron oxide. I just want to say that the predictions are in good agreement with the data, and therefore the model can be used for predicting burn rates with aluminum catalysts and inhibitors of various kinds. Okay. More predictions and comparison with data. The agreement with experiments is good, excellent to reasonable. Note that AL distribution is available only for the Space Shuttle booster. For other cases, it has been assumed that all the aluminum is conventional aluminum, especially in the case of 15 to 18 micron aluminum and the 25 micron case. In the case of 5.65 micron aluminum, it was assumed that there is a small fraction of it which is smaller than 1 micron, which contributes to some heat flux at the surface to explain the observed burn rates. Okay. So, assumed distributions for aluminum has been used to obtain predictions for propellants from Dokan et al. And Verma and Ramakrishna. In case of the propellants from the paper by Doken, AP distribution for 10 micron nominal size was assumed to be log normal with 1 micron standard deviation. The point I want to make is that when you want the predictions to be good enough for you to make decisions on which composition to go forward with, the important information that the important inputs that are required for the code are detailed AP particle size distribution and also detailed aluminum particle size distribution, just to make sure that just to find out what fraction of the particles are smaller than 1 micron and what fraction of the particles are larger than 1 micron. It looks like if the aluminum nominal size is between 15 and 18 micron, then the fraction that is smaller than 1 micron is negligible. But if it is 5 micron or 3 micron, as we saw earlier, it could be significant. Again, more predictions for conventional aluminum. I do not want to go into the details. Again, more predictions. That is how the effect of conventional aluminum is accounted for in the model, essentially saying that there is no effect. Okay. But it is not the case when we have submicron or ultrafine or nano or flaky aluminum. All these aluminum particles can burn close enough to the surface, contributing to the heat flux. What is done in this case is that all submicron aluminum is homogenized with the binder and hence becomes part of the binder matrix. This formula we saw earlier. All that is done is the aluminum is also homogenized with the binder. It is fine enough to be considered homogenized, and it is homogenized with the binder while estimating the thermochemical properties and the binder thickness and the oxidizer to fuel ratio, and therefore the thermochemical properties also. Radiation assumed to be decoupled from conduction, therefore the contributions from conduction and radiation are taken to be additive, and therefore the heat flux balance at the surface has an additive radiation term in addition to the convective heat flux that comes from the gas phase. So the burn rate equation will get modified with the radiation term getting incorporated here. Geometric description and statistical particle paths are calculated using the same methods as for AP HTPB propellants. It is essentially the same. This is an important point. Remember that all AP particle sizes are coated with the same thickness of binder matrix. Okay. What it means is that a 400 micron particle or a coarse particle will have, in proportion to the amount of AP, will have less binder and therefore less aluminum also, compared to a particle, let us say, is 100 microns or 80 microns. Okay. So this is a particular case where the propellant is a bimodal propellant with 400 micron AP and 82.5 micron AP. So the 400 micron AP particle here contains 83.5% AP and 10% total aluminum. On the other hand, 82.5 micron AP will have 44% AP and 34.5% aluminum. This is the same thing can happen for inhibitors and catalysts also, because the inhibitors and catalysts are also added to the binder, and therefore the amount of catalyst in proportion to the amount of AP present will be much smaller for coarse particles compared to fine particles. And this is the reason why when you use the same catalyst, but when you change the coarse AP to fine AP ratio in a propellant, the relative increase in burn rate or the incremental increase in burn rate can be different. So the AP and aluminum mass fraction and flame temperature distribution in the 400 micron 82.5 micron, which is in the fraction of 80 to 20 from Doken et al. Is calculated here, and the important conclusion is this, that the amount of AP and aluminum are very different for coarse particles and fine particles. A simple model is adopted for the radiation. I will not go into the details. I want to just emphasize that the radiative flux depends on the surface area which is radiating, okay, and here the surface area is dependent on the number of particles, and if these two effects are accounted for, the final expression for radiation will show that the radiative flux that comes to the surface is inversely proportional to the size of aluminum, which is consistent with our expectation that smaller the aluminum particle size, larger is the radiation contribution from the aluminum particles. Okay. So note the inverse dependence on AL particle size. The variation of path length can be interpreted as a variation in the effective number of particles radiating into the propellant surface. Another effect that needs to be accounted for accurate prediction is smaller particles tend to agglomerate. Even if you are careful to avoid agglomeration when these particles are getting integrated into the propellant, when they come out of the surface they will agglomerate. These particles will agglomerate. Okay. Larger AL particles do not play an active role in processes close to the surface, but ultrafine aluminum particles increase the burn rates by a factor of at least 2 to as high as 5. This clearly shows that agglomeration effects dominate beyond a critical number density, because if you do not account for agglomeration, the burn rates that you get must be much higher than a factor of 2 to 5, and therefore is taken to be proportional to the reduced number density beyond the critical value. So the critical value is calculated from the predicted burn rates. We make a prediction without accounting for agglomeration. It matches with the data only when the fraction of the ultrafine aluminum is below a certain critical value, and that number is taken to be the critical number density for agglomeration, beyond which agglomeration will become important. Okay. That is what is shown here. The critical number here is obtained for this. Here the critical number is for the case with 20% ultrafine aluminum and 80% conventional aluminum. The critical number is 6.6 times 10 raised to 19 particles per meter cube, and when the number goes beyond this must be 2.6 into 10 raised to 20, not 10 raised to 19. When this number goes beyond this, the extent of agglomeration is taken to be the ratio of the number densities. Similarly here, at 20% ultrafine aluminum, the number density is 1.4 times 10 raised to 20. It increases to 7 times 10 raised to 20 when you go to all ultrafine aluminum. Okay. So the conclusion is that, one, it is difficult to process with 100% ultrafine aluminum or 18%, which is the absolute number. The other thing is that the enhancement in the burn rate that you will get may not be very significant, because by adding more ultrafine aluminum you are increasing the number density and more particles will agglomerate, and the relative increase in burn rate at some point will saturate. Okay. So maybe you are better off with some substitution of conventional aluminum by ultrafine aluminum instead of replacing all the conventional aluminum with ultrafine aluminum. That is the conclusion from the effects of agglomeration and the relative number densities. This is the experimental data set that is used for validating the approach shown here. The MATLAB code, which the MATLAB code implementing the software is implementing the theory is extended to include the aluminum model. Results, I just want to say that the predictions are in good comparison with data, but the critical number density is an input that is required for this model, and therefore the assessment of the enhancement in the burn rate because of addition of ultrafine aluminum requires systematic substitution at different levels, so that the critical number density can also be evaluated. Okay. The question is, the hypothesis was the radiation that contributes to the increase in the burn rate. This is just to show that it is indeed radiation that contributes to the observed increase in burn rate. In fact, the numbers are pretty high. What is shown here on the left is the radiation, the magnitude of different terms in the surface heat balance equation for a case that has 18%, 30%, 18% 30 micron aluminum and 0% nano aluminum, all the way up to no 30 micron aluminum or no conventional aluminum and all ultrafine aluminum. Okay. So this is the conventional propellant where the radiation is negligible and all the other terms balance each other, and the magnitude of the flux is about 10 to 15 megawatts per meter square. Okay. And as we substitute, as the conventional aluminum is replaced by ultrafine aluminum, the radiation flux goes up significantly. In fact, it goes up so much that the convective flux becomes negligible in comparison to that, and the surface heat balance is simply between the radiative flux, the surface heat release, and the flux that goes into the condensed phase. Okay. As the fraction of nano aluminum is increased to 18%, all nano aluminum. Look at the flux that is coming to the surface, it is 125 megawatts per meter square, okay, that is 10 times as high as what you would get in a conventional aluminum, a conventional propellant with conventional aluminum, okay. And the heating rates that will be experienced by the propellant surface will be 100,000 kelvins per second or much more than that. It might be 100,000 kelvins per second, even here it might be an order of magnitude higher in this case. Okay. The same thing is shown, this is for the 400 micron particle, this is for the 82.5 micron particle. The effects are not as dramatic as it is here, because this particle size is fuel rich and therefore the overall temperatures are not as high as it is here. Again, flaky aluminum can also be accounted for, the effects of flaky aluminum can also be accounted for in this model. I just want to mention that the predictions are in good comparison with the data for spherical denoted by S and also flaky aluminum. So, the summary of this part is that the theoretical model for predicting the burn rates is extended to account for the effect of aluminum. The MATLAB implementation of the model is now available with DRDL, HMRL and VSSE for integration into the design process and further collaborative development. Predictions for conventional and submicron aluminum has been shown to be excellent to good. The theory can be extended in a straightforward way to capture unsteady effects also, and this is what I want to discuss in the next section, but before we go there, if there are any questions, I will be happy to answer in this part. Yeah.
There are two questions. What is the typical percentage of aluminum particles for agglomeration? Is it only depend on the percentage, or it also depends on the surface temperature?
Well, it depends on the percentage, it depends on the size, it depends on the percentage, it depends on the number density, and it may also depend on the temperature. But the fraction and the size effect seems to be the most important, because close to the surface temperatures are roughly the same, about 1200 kelvins. So, the number, the fraction and the size effect comes because for a given fraction the same effect as atomizing a spray. So, if you have a 1 mm droplet, you break it down into same volume into 10 micron droplets, the number of particles that are there are much higher. Similarly, here if you have the same mass with 30 micron aluminum and 0.1 micron aluminum, the number of particles with 0.1 micron aluminum is much higher than what it is with 30 micron aluminum. And that means that you have a large number of very small particles that are close to each other. Smaller the particles, there are also other effects, surface dominated effects that come into picture.
Radiation we have shown is without considering any agglomeration.
It is with agglomeration. The agglomeration effect is what is shown here.
So radiation effects we have shown for all ultrafine particles.
All ultrafine particles accounting for agglomeration.
After accounting for agglomeration,
The effective particle size that is taken to radiate to the surface is calculated after correcting for agglomeration.
then the burn rate should increase. No?
It is increasing.
But what you have said in the first slide is, if I am changing from 18% conventional aluminum to completely ultrafine aluminum, the increase is not that effective.
That is not what I said. No, that is not what I said. If you go from conventional aluminum to all ultrafine aluminum, the increase in burn rate is 5 times.
5 times.
Dramatic.
Yeah.
Dramatic is the word that is appropriate for describing it. What I said was, if there was no agglomeration, you would have gotten a much higher increase in burn rate. It is only 5 times here. If there was no agglomeration, you would have probably got 10 times increase in burn rate. And therefore, simply increasing the amount of ultrafine aluminum because of agglomeration will not give you, a proportional increase in burn rate, because the effective particle size that is radiating will increase as you increase the fraction.
I thought that this is not accounting. This graph has shown this.
This is experimental data, by the way.
With the experimental data and model, what you said, I thought you are not including agglomeration, but you are including agglomeration.
Agglomeration is included. That is what is in this slide. The effective size is taken to be the actual size multiplied by the actual number density divided by the critical number density. Therefore, at the critical point you will have the same size radiating. At higher fractions there will be a larger AP particle, a larger aluminum particle radiates to the surface. That is the effect of agglomeration, or rather that is how the effect of agglomeration is accounted for in this model. Yes sir.
This particle size that you have been emphasizing on submicron particles.
Yeah.
How will you evaluate the particle size?
Uh,
We are using, sir.
sorry.
What's the technique used in particles?
I think all I want to say is some light scattering techniques.
Laser diffraction.
Yeah.
We
Some
use laser diffraction.
laser diffraction. So one of the light scattering techniques. Yeah. Any of the light scattering techniques probably requires a better resolution than the commonly available equipment. But that is what will be used. Yeah.
The second thing is that we have log normal distribution like Fukuyama, Kanazawa, lot of distributions. So are they having any bias towards the measuring problem?
Well, it looks like when you start, see there are these particles are synthesized by a certain methodology, and there is a large number of independent random processes that are happening during the synthesis as well as grinding, and therefore analysis of particle sizes of different kinds of materials, ammonium perchlorate, aluminum, droplet size distributions from sprays, all seem to be very close to a log normal distribution. So,
More random, there's no bias towards any
the logarithm of the diameter is normally distributed. If you ask me why the diameter itself is not normally distributed, I don't know. But I would assume that there is some role of central limit theorem that is making these distributions normal in logarithm of that parameter. If there is a universality to it, I guess there is a universality to it, just that I do not know what it is.
There may be some fundamental physics playing role.
I am sure.
We are not really exploring.
Yeah. Right. The answer might also be there, just that I do not know. Yeah.
Sir, in the slide in which you talked about thermochemistry, based on the so here like this thing like 83% AP and 10% aluminium, and then when you go for a lower sized particle size like a less coarser AP, we have the percentage of aluminium increases. So this thing has been used as an analogy from the experiments we had, or there's some other basis for this thing?
This is simply based on the way the binder matrix is distributed in this model.
No, how this thing that if we have a bimodal distribution for a less coarser AP, we'll be having the binder matrix will be more rich in aluminium as compared to
the binder matrix is not more rich in aluminum. The binder matrix composition is uniform.
Whatever surrounds that.
No, the binder matrix composition is uniform. See, the binder matrix is composed of fine plus the extinct AP. This we saw earlier, plus all the HTPB, including all the agents that are used for curing and cross-linking, everything. Okay, this is, I'll put the HTPB within quotes because I am not referring to the monomer resin or something like that. It's the entire fuel binder, okay, plus fine aluminum. Okay. This is the binder matrix, and therefore the composition of the binder matrix is fixed. It's the same. The reason why coarser particles have smaller amounts of binder and smaller particles have larger amounts of binder is because we coat them with the same thickness. Coat them with the same thickness. I want you to imagine that this thickness is same as this thickness. Okay? Just that this now will have lot more binder than AP. You may ask, what is the basis for this? There is some experimental evidence that suggests that this approximation is okay, but what I would say is that assuming this gives us a certain oxidizer to fuel ratio, which says that the distribution is very wide, that there are particles which are almost pure AP, there are particles half of it is binder. This seems to be that the predictions are in good match with data, seems to indicate that this is closer to reality when it comes to the oxidizer to fuel distribution within the heterogeneous propellant. Okay. Of course, we could have, we can try many things. I can assume that the thickness is proportional to the diameter, the thickness is proportional to the surface area, all that is possible. But this simple approximation or the simple assumption seems to be in agreement with reality, data from reality. Any other questions?